Hello everyone, I am Pushpita Chanda. I am a PhD student at IIT Delhi under Equator program. I am a TA for this course Newtonian Mechanics with examples. This is an extra tutorial class because I wanted to discuss some additional problems on the Newton's law section, and also some problems which I have not discussed yet, that is some collision problems and some virtual work problem. So let us begin. So first we will discuss collision problem. Like basic collision problems. In type of have to know before the collision problem how many type of collision is there and what is their properties. One is elastic collision, second is inelastic collision. In elastic collision, kinetic energy and uh, momentum both are conserved. But for inelastic collision, we can only apply conservation of momentum, but not the conservation of kinetic energy. So how we extinguish that the collision in elastic or inelastic? If like for collision is elastic, then the problem is in explicitly mentioned in most cases that collision is elastic. However, if the collision is inelastic, then it may be explicitly mentioned, or phrases like there is loss of kinetic energy or breaking of objects and objects stick to each other are used. So for a perfectly elastic collision, objects stick to each other. Collision. Thing that we need to remind, that is coefficient of restitution. This E is equal to velocity of separation after collision velocity by velocity of approach before collision. So the E varies between 0 to 1. So what happened that if for inelastic collision, criteria, okay. So for elastic collision, E is equal to 1. For perfect inelastic collision, E is equal to 0. And for E vary from 1, they are all some kind of elastic equation. So after that, like I want to derive an equation which I will do very quickly. For elastic collision, sorry, we know there will be kinetic energy conserved and momentum will also conserve. So this is particle M1, M2, So before the collision, like for the simplicity of equation, the velocity in the same direction, okay? Then they collide. Then again they move with another velocity. So we have taken u1, u2, v1, v2 in the same direction because so that we don't need to like incorporate negative thing in the like formula. So when will be like if there is no like one particle is in positive x, going in positive x direction and another is going in negative x direction, then what happened then you need to like put a positive x or like plus sign and minus sign. So this is m1 m2, this is m1 m2. So when the conservation of momentum happened, then m1 u1 plus conservation to u is equal to m1 v1 plus v, and conservation of kinetic energy half of m1 u1 square plus half of m2 u2 square is equal to half of m2 v2 square plus half of m1 v1 square. From this new equation, you can also solve it in your home. What I will write that v1 is basically u1 m1 minus m2 plus 2 m2 u2 by m1 plus m2, and v2 is basically u2 m1 minus, sorry, here m2 minus m1 plus 2 m1 u1 m1 plus m2. So you can see that in special, like if you if in the question they say that the two object of masses something something moving with speed u and to u in opposite direction, then if you take u plus u1 will be plus u2 will be minus u in opposite direction or something. So according to question you need to check the sign. So there is special cases when Okay, so in 1D cases, okay, first of all, you need to remember this is 1D collision we are talking about. 2D, you need to concept momentum in a momentum in both direction. So if m1 is equal to m2, then it becomes v1 becomes u2 and v2 becomes u1 after collision. And if one object is if one object is much bigger than another, say m1 is much bigger than m2, then and u1 is the special case, then v1 became 0 and v2 became minus u2. And when that happened, example is a ball is hitting a wall, so it will hit and go back in the same with velocity. And there is elastic, this was one dimension. For elastic collision in 2D in lab frame, so this is A, say this is B, and after collision moves in this direction A and another moves in this direction B. So this is basically theta 1, this is theta 2. We need to write the conservation rules, that is half of m, and we assume that one of is in rest, like the B, this is before picture and this is after picture, and they are of the same mass and B is in rest. So these are the special cases. So velocity of A was v, and now we have the velocity v1 and v2. So half of mv square is equal to half of m v1 square plus half of m v2 square. So from here we can see this is v square is equal to v1 square plus v2 square. From conservation momentum, x direction, get with v V was in that direction, so there is no different x and y component for V there. So that is V is equal to V1 cos theta 1 plus V2 theta 2. This is question 2. And in y direction, get, we can write m's here. M will be cancelled out. So in y direction, the before the collision there was no component, and after the collision in v1 sine theta 1, and this both of them has x component in this direction. One have y component in positive y direction, and this have y component in negative y direction. So we have v1 in v2 sine theta 2. So from here we get that v1 is equal to v2 sine theta 2 by sine theta 1. This is 3. Now putting 3 in equation 2, we will have v2 is equal to v sine theta 2 sine v2 is v sine theta 1 by sine theta 1 plus theta 2. Basically, when then we can show like in a further calculation that sine theta 1 plus theta 2 is always pi by 2 for a elastic collision in 2D when one mass is at rest and both of the mass is like of this have same like mass component. That's the thing. And there is another thing called perfectly inelastic collision. For that, what happened that, say this is M1 moving with U1, and this is M2, this is before. After the collision, both stick M1, M2, and both are going with the same velocity V. This is called perfectly inelastic collision. So for that sense, velocity v becomes m1 u1 plus m2 u2 by m1 plus m2, and the difference is kinetic energy, that kinetic energy initial and kinetic energy final, that is become half of m1 u1 square plus half of m2 u2 square minus half of m1 plus m2 v square, and put the value v here, we get that is basically m1 m2 u1 minus u2 whole square by 2 m1 plus m2. Okay. Question 1 for collision is two particles A and B of mass m and one particle C of mass capital M are kept on the x axis in the order ABC. Particle A is given a velocity vi. Consequently, there are two collisions. Both of which are completely inelastic. If the net energy because of these collisions is 7 by 8 of the initial energy, the value of m in terms of small m. So basically, we need to read the question and respond that way. That A, B, C are kept on x-axis, kept. That mean initial velocity is 0. Only one has the velocity, and the particle 1 is given a velocity. Other people were not like other particle did not have any velocity. So basically what happened, this is B, this is C, this is A. A was given a velocity A, and both the collisions are inelastic. A like collide with B and stick, and it became A plus B plus C, and that's why they were moving. Time. momentum conservation get m small v, and after two collision both are inelastic, the mass became 2m plus capital M v dash, and loss of kinetic energy is 7 by 8 of initial kinetic. Initial kinetic energy was mv square. So this is basically half of 2m plus capital M v dash square minus so this is basically half of mv square minus half of 2 small m plus m v dash square. So 7 by 60 mv square is equal to half of mv square minus half of 2 small m by capital M v dash square. And we know v dash is equal to mv by 2m plus capital M. Putting all this value where So basically, half of mv square minus half of u small m capital M v dash square is equal to 7 by 16 mv square. And now we will put the value from v dash we get here, that is m v by 2 small m plus capital M. So putting all this value here to use, we get 7 by 16 is equal to half minus half of m by 2 small m by capital M. Okay. 7 by 8, 1 minus m 2 small m plus capital M. By 8. So 8m is equal to 2m plus m. So m is equal to 6. That is our answer. Question 2. A particle is released from some line T. It breaks into two equal parts. Horizontally with speed equal to half of the speed So it says the particle is released from some height after time t. It breaks up into two parts. So the one of which lies horizontally, which speed is equal to the half of the speed. So basically at t is equal to 0, the particle is this. When the particle reaches here, so basically one particle has horizontal component and another particle will have vertical component and something. So basically we will say that momentum will conserve and particle breaks into, so we are not using conservation of kinetic energy, only momentum energy. So as the particle mg in this direction, so mg into p, acceleration into time velocity, and into j direction, that is initial, and final is the particle breaks into two, and particle says that the particle has a velocity half of the before breaking it. So before breaking it, its velocity was it will be to gt by 2 I, because the horizontal component, and we need to decide what is this v. So v is basically 2gt. From this equation you can say this is v, and the value of v is root over 2gt by 4 whole square plus 2gt whole square, and that is root over 17 by 2 gt. It is very simple question. Just you need to do it in a vector approach. That's it. Number 3 is a ball hits a wall velocity 20 meters per second at an angle of 60 degree and rebounds at an angle at 30 degree with the one. Calculate the coefficient of restitution. So this is the ball. So it hits at 60 degree and goes back at 30 degree. So momentum will conserve. So in the velocity is 20, so mv, and the wall hasn't moved. So it is basically Paul's velocity. So m going the in x direction, in y direction they compensate each other. So m to the cos 60 degree. Sorry, we are only taking the y direction. So cos 60 degree in this direction is equal to mv cos 30 degree, because we need to calculate this velocity because to calculate E, this is after the separation, the velocity of separation, we need this thing, velocity of approach. Even we would have taken the like y sine theta component, we will get v the same. So we need only, so this is v sine 30 degree, this is 20 sine 60 degree. Yeah. So meter per second. Putting this value, v sine 30 degree, this is 2 sine 60 degree. So basically, this is 20 by 2, 3 sine 30 degree is half. But 20 by 2, 5 3 by 2, this is 1 by 3. So sheet of this 3 with 1 by 3, and this is the inelastic collision, we can see that. So now we move to virtual work, principle of virtual work problems. Put there. We'll discuss so principle of virtual work only work when the system is in static equilibrium. So for principle of virtual work, this is question 1. The mass M is So basically where it says the mass m, this is the m, is brought to an equilibrium position by the application of torque m at the end of one of the parallel links. So this is the system, and determine the expression of the equilibrium angle theta, that is the sine theta in terms of links, and this is the theta between links and the vertical for a given value of m. So this is the case, and we will use the principle of virtual work to do that. Okay, so basically here everything is given. This is G. So mg is working in this direction. So there we like assume the distance between this and this is h, and this is c. So the work mg during a movement delta h in the direction of mg. So according to principle of virtual work, mg delta h will be mg delta. So we know delta h is, this is b cos theta plus c. So this is b cos theta plus c, and when we operate delta, it will be minus b sin theta delta theta plus c. So it's basically c, not c, delta c is equal to 0. So this is basically minus mgb sin theta delta theta. It's working. It's negative for a positive value of delta theta. If delta theta is positive, h is negative. Now the work done by the clockwise couple m is m delta theta. So m delta theta plus mg delta h should be 0. This is because of principle of virtual work. So there is only two external when the system in static equilibrium. This is delta R is equal to 0. So the work done by the external work, the virtual work done by the external force is 0. So here are two force, external force m delta theta plus m delta h. So we know what is equal to m delta h. So m delta theta is equal to minus mg delta h. So mg minus b sin theta delta theta. So that is mgb sin theta theta Sin tilde theta delta theta will cancel out in the m by s. Theta is equal to sin inverse m g. This is answer. Question number 2. Let me write the question, then I can start. So the question is the portable car hoist. This is the portable car hoist that is operated by a hydraulic cylinder. This is the hydraulic cylinder which controls in the horizontal movement of end A. So this hydraulic cylinder controls the horizontal movement of A, and so we need to determine the compression C in the piston. Here in the compression in the piston rod of the cylinder to support the load. Here the load is at here P at height HA. That's our question. So we will use principle of virtual work to solve that thing. So we first do a free body diagram. So basically free body diagram is this. So the compression C works in this direction. It's B. Here P is working in downward direction. This is B. This is also B here to be then of the same inside. I could say. I was confused. So this is B and this is B also. This is theta. So using principle of virtual work, we know the work by the external virtual work by the external force needs to be 0. So here, due to C, if we like the due to the compression of C, the A end of A the, due to the compression of C, this A moves. So A moves delta X. So this is the X direction. So C delta X plus P. So when this moves, P also moves in this direction. So basically we take this is the positive X and this is the negative X. So delta A moves in this direction. So we give right minus C delta X minus P delta H is equal to 0. And what is X? This is B cos theta. So this is B cos theta and this is B cos theta. So C is and X is 2B cos theta. And H, we can see that H is B sin theta. So this is B sin theta is here. This is B sin theta and this is also B. So this is theta also. So this is also B sin theta. So this is 2B sin theta. So delta X is minus 2B sin theta d theta and delta H is minus plus 2B cos theta d theta. So putting this value previous equation, C delta X minus P delta H is equal to 0 become minus C minus 2B sin theta delta theta minus P 2B cos theta delta theta is equal to 0. So this is 2B C sin theta minus 2B P cos theta is equal to 0. So C is equal to P cot. So we need to calculate, this is theta. So we need to calculate tan theta. So tan theta is basically half of h by half of x by half of h by half of x. So tan theta is equal to h by x. So this is basically half of, so this becomes h by x. So cot theta will be x by h. So x is basically 4b square minus h square by h. So this is basically 4b square minus h square by h. You can write it as a to b by h whole square minus 1. So this is 2b, this is h square, so you know h square plus x square is equal to 2b whole square. From this we get x is equal to 2b minus h whole square. 2b square minus h square. It's question 3. Determine the force P required to maintain the equilibrium of the linkage. Sure. So this A and B goes freely in this horizontal road, and we need to determine this force P to require to balance all this force. So basically, we draw our diagram again. So the value P here, This is 75 Newton. This is 150 Newton. This is D here. This is 100 Newton. And from here, it's 400 Newton. This is A, B, C, D, E. This must be F. So all the linkages are of the same length. So if we take this is YC, this will be 2YC. This 3YC. So this is YD basically. 3YC is equal to YF. YG is equal to YH is equal to 4YC. Please wait a minute. We have a glitch again. So this is if they are all the same length. So this is YC. This is must be 2YC. This is 3YC. this is 4yc. So yd is equal to 2yc. yd and ye is same. yf is equal to 3yc, and yg ya is equal to 4yc. So we now apply principle of virtual work. Delta u is equal to 0. So delta u is nothing but f external delta I equal to 0. So here the external force are 100 Newton, 75 Newton, 150 Newton, and this speed. So it's 400 Newton also. So 400 yc plus 100 delta yd minus p delta yf plus 75 delta delta yg plus 150 delta yh. So delta yc delta yd is equal to delta 4 into yc. So 4 yc. Sorry, this is 2. Delta yf is equal to 3 delta yc. Delta yg is equal to delta yh is equal to 4 delta yc. So this is yc, this is 200 delta yd, this is 3p delta yc plus 4 into 75 is 375 plus 150 into 4 delta yc. This is all equal to 0. So basically (900) delta yc is equal to 0. So 1500 delta yc is equal to 3p delta yc. So p is equal to 500. Question 4. So the question 4 is the So this the rod AB is attached to the collar. This is the rod. A and rates are not small wheel C. Neglecting the radius of the wheel and affected friction, derive an expression for the magnitude of the force Q. This is the Q required to maintain the equilibrium of the rod, and there is a force P is working. So first the free body diagram. So basically this is a rod AB, this is C. Ignore the radius and the friction, so we ignore. This is theta, this is also theta, this is Q, and this is P. So because of the wheel C is working in this direction, so this thing and this thing we assume this is A. We don't need to assume this is given good. A dash. So this is A. So this is A also. So A dash C by A is equal to tan theta. So A dash C is equal to A tan theta. So this is the y of A. So we call it is a baseline. This is 0. So y is equal to minus A dash C. And this is YB. YB is equal to BC dash. Whole thing is L. So this is L sin theta. So basically this is L sin theta minus A dash C. So YA is equal to minus A dash C. So minus A tan theta. So delta YA. We need YA when YB because P is acting at the end of the B and Q is acting at the end of the A. So delta YA become minus A sec square delta theta. So that is basically y cos theta delta theta. YB is equal to BC dash, that is basically L sin theta minus A dash C. So that is L sin theta minus A tan theta. Delta by B is equal to L cos theta delta theta minus A cos square theta delta theta. So now applying the principle of virtual work, we know that both the things minus Q delta by A minus B delta by B should be 0 because both are working in the negative y direction. Minus Q. Now putting the value of all those things there. The answer. This is question 5. Spring of constant one question is the spring of contact in the spring of constant K is unstretched when theta is equal to 0. Derive an expression for the force P. This is the P required to deflate the system to angle theta. The masses of the bars, this bars are negligible. So the to calculate these bars, like take into account the mass of the bars. Situation is here. This is rolling. This is y. Both the bar is same. This is L. This is theta. This is theta. This is P. This is the free body diagram. So according to principle of what you want, delta is equal to 0. So P is working here. So this is the x direction. So P into delta x will be K into L minus L cos theta delta y z. For this being f is equal to kx. So x is basically this is L. So this is L cos theta and this is L cos theta. So this is 2L, and when there will be when theta is not equal to 0, this is 2L cos theta. So this is difference between the when this is stretched and this is not stretched. So we know x is equal to L sin theta, y is equal to 2L minus 2L cos theta. So delta x is equal to L cos theta d theta. Delta y is equal to L minus z plus sin theta. Okay. Now substituting these values in this equation. Now we need to solve this equation. Is 3 cos theta. That is equal to 4k square. Sin theta minus 4k L square sin theta cos theta. So E is equal to 4k L square sin theta minus 4k L square sin theta cos theta by L cos theta. So we will have 4k L tan theta minus sin theta. This is the answer. So that is how we can easily solve systems problem with virtual principle of virtual work. Now we will solve 2 or 3 like Newton's problem, like problem with Newton's law. And this is 250 Newton. The question is, so we need to calculate the moment of this 250 Newton force on the handle. This is the handle of the monkey cage above the center of the bolt. So we need to draw a free body diagram. This is a too complicated like so draw this is O, equivalent of this is a O, and the force is 250 here. So this is Fxv and this is say Fy. So this is 30 millimeter, so 0.03 meter. It's 0.2 meter. So Fx is equal to F sine 15 degree. So F is 250 sine 15 degree. That would be 64.7 Newton. And this is Fy, which is F cos 15 degree. So 250 cos 15 degree. This is 241.48 Newton. So we need to calculate the moment about O. Fx into 0.03 is x. So this is O. This is the like working axis of Fx, and this is the working axis of Fy. The moment is difference like in opposite direction due to Fx and Fy. So this is Fy into 0.2. So Fx is 64.7 into 0.03 plus this is between 4.48 into 0. Sorry. Point. So when we calculate this thing, it will become 46.36 meter. This is the moment. Now we have a similar question. Mechanic force on the 13 millimeter combination. The 140 Newton force shown. Determine the moment of this force. The center O. This is O. So first to draw some figure diagram. So this is 0. This is 15 degrees. And then this is 25 degrees. This is 140 Newton. And about O, so the distance is 0.95 meter. So moment O is F cos theta. This is F, and we need to Newton angle theta. So F cos theta is 0.95. That will be 25 minus 15. Degree. So that would be 140 cos 10 degree into 0.095. 13.1 nanometer. So like there we can discuss the last problem here. It's the problem. This is question 3. The question 3 is that the portion of the mechanical coins sorter works as follows. Pennies and dimes roll down the, let me write. So basically, the question is the portion of a mechanical coin sorter works as follows: that pennies and dimes are rolled down 20-degree incline. This is the 20-degree incline plane. The last triangular portion of which, this is the pivot. Like when the pennies, when the dimes roll enough, the dimes are lightweight, so it remains stationary. So this falls into there. But when the pennies come to this portion, this becomes movable, and this moves in a clockwise direction. So the pennies fall into there. So we have to determine the moment about O, that is the O of the weight of the penny in terms of the slant distance s in millimeters. So this is the slant distance in millimeters. So first, free body diagram. So we need to draw a free body diagram now. This is 20 degree. This is O. This is S. Okay. Point 0.035 meter or 3.5. Sorry. This is 3.5 millimeter. So mg in this direction, mg is working. So this is also 20 degree. So this is mg cos 20 degree, and this is mg sin 20 degree. So about O, we took all the fluid, like moment. So mg cos 20 degree works at distance s, and mg sin 20 degree distance of 9.5 plus 3.5 meter. So here mg is 3.06 because they have asked to calculate in terms of penny. So 10 into cos 20 degree into s plus 8.06 into 10 sin 20 degree into 10 to the power 4 because 110 is for gravity and 10 to the power 3 is for the in gram, in them in kg. So that would be 30 Newton into millimeter. So will be 0.0282 s plus 0.1335 Newton millimeter. So these are some moments of the you have seen that there were many kind of problems there. So you have to practice whatever discussed in the lectures and in the assignment, and similar problems we have discussed in both in my um, sessions and also the other PS session. Just go through it and it will be fine. Thank you and all the best.